Okay. So.
Recording in progress.
Oh, thanks. It's always Sunil who is starting it, yeah. So, thanks Didier for kind introduction. And thanks all other speakers who did already great job. And I have a problem now. So the idea of my talk is to show you some ingredients which you need for the spectroscopies, which you will definitely meet when you will do hands-on course, and if you are interested to do the spectroscopy. And then there were already some questions during some people were asking me about the DMFT, about temperature dependence, how it looks when we do it in ARPES, about full potential, like he is interested. So that's why I decided maybe it will be a bit chaotic talk in the terms of topics, but I already, because we had a really beautiful introductions, and that's why I was more thinking to do it more in a way that you see different ingredients which are needed, which are then valid for many spectroscopies, many scattering experiments, and it might maybe help you then for this hands-on course, that you will realize in the code there is a matrix element which we call gradient V. What does it mean? You know, but this you need for many with many aspects. That's why here is the outline. So surely, you know, most of the thing was already said, so I will repeat many things, and then at the end I will come to the correlation effects, to the DMFT, then to final states effects, because that was also already a bit question what it means when you go to high energies. Do we really need to take some special final state and not enough? It's not enough free electron-like state. I will show you some example. We'll go to temperature effects and some matrix elements effects, depending on the time. So let me start with the motivation. Certainly, all of us here, because we are looking for the electronic structure, magnetism, spectroscopy. We have experimental colleagues here from Swiss Light Source, for example, from Würzburg doing photoemission and others. Then we have here also many people doing electronic structure calculations, the standard ones. I mean, I would call it from kind of, we work all of us with the DFT, but we are looking all of us to the electrons, and we want to see them in the different cases. We want to have a look to the relativistic effect, to the charge degrees of freedom. We want to have a look to the interfaces, what is happening, want to look to the spin of the electrons, and then at the end of the day understand. And now certainly this I like, this is Ondra's typical slide, so because he likes to make easy slides. So we want to now to study those electrons which are kind of clue in our system. And so we have a black box and we have some input, we are looking to the output, and we want our spectroscopy is to investigate these properties and as much as possible to get about the ground state and then to understand certain topics. So my favorite spectroscopy right now is the photoemission. And just as a motivation, so photoemission, you know, you have a photon source, you have a light, monochromatic light, you shine it on the sample, and you collect and measure the kinetic energy of the photoelectron, its angular dependency, so the momentum. You can measure the spin information, and now depending where you are in your photon energy or in the kinetic energy case, you can look, for example, to the core state. You can have a look to the so-called chemical shift, which is the simplest possible interpretation. This is a nickel-doped strontium titanate, where you nicely see some nickel states over here, and so you can analyze it. When you go to the angle integrated case, you can do the same, but you can then, the simplest interpretation is the density of states. Or when we go to spaghetti, so to angular result photoemission, the simplest interpretation is the spectral function, as we saw it already, and you can have these bands. So you can look to the band structure. So as I said, all of these are the data which Fatima measured. So it's nickel-doped strontium titanate. But this is not always enough. And now if you want to do it, Maybe what is a bit special on our approach also in Pilsen is that we are doing also experimental part of the job sometimes. So we build up the ARPES laboratory. We had a bit problem to put it in. I was looking for what we got delivered for this money. And we have a machine which is over here. It is theoretician proved, I can say, because I tried to do some experiments. And Laurent, who is responsible for, he will say no, but I did something, at least XPS by myself. So if you are interested also to get this kind of, do some experiments also, just let us know. So that's, I would want to show it to you in a sense, because if you are doing theory and you would like also to get hands-on on this, just let us know. So, and it makes a happy people, so Laurent and Sunil. So, no, but let's come back to the thing. So as I said, at least, for example, in the photoemission, but this is true in many spectroscopies, the simplest interpretation, which you know maybe from the textbook, which is then simplified as far as possible, is not many times enough. So here I'm showing you the Fermi surface of this potassium-doped iron isonate. So it's iron pnictide. It is a kind of prototypical high-temperature iron-based superconductor. You measure this Fermi surface. You see some spherical features here, some propeller-like feature. You see that at the X point you don't see anything. Now, when you do the DFT calculations, doesn't matter which code, your preferable one, you will realize that at least around the gamma point, you could see that you can compare it, but at the second gamma bar point, which should be this Z point, it's not comparable. Only when you do really full calculation, then including various aspects, you can then compare it and you can understand what is happening around. And this is true in many ways, and you need to have a material-specific input to do such calculations, and you have to have. We are here because we are using flexible method, the KKR method. You know, we need to include disorder here. You heard already the CPA because we have a very doped system here. And then you go to photoemission. There are various aspects which are partially connected to photoemission itself, but to many other spectroscopies as well, like temperature effects, which John will also speak about, matrix elements effects, correlation effects. We will hear as well in several talks in the spectroscopy part. And the people there, they will go more to the details of a given spectroscopy. So now, why multiple scattering? Let me start our favorite way how we see it. We start with the many-muddy ground state, we map it to the DFT. I realized actually afterwards that we didn't go to the density functional theory, we didn't have a talk about this, but I hope most of you know it and have a basic idea. So we mapped the many-body problem to one effective particle problem. We can then use a periodic lattice, or we can do real space, as we saw in case talk. We can get the band structure methods, or we can go beyond with the big plus. We can use DMFT, we can do GW, we can do Cumulant expansion, and so on to understand, to improve the missing effects which are not in the DFT present. And the DFT, there are two things which are not present. One thing is density functional theory. We are using certain functionals which are approximative. And this is true for ground state, and we are missing some effects already in the ground state level. But we are missing also in the excited state some levels, because DFT, it's a ground state theory. So we need to improve it also on that level. So there are two levels with respect to spectroscopy, which you have to take into account. And you have to look some effects, it's enough to improve on the DFT, so on the ground state level, but some not. You need to really have an excited state to catch it, like plasmons, for example. So so that means we end up with some effective equation to be solved on Sham, Schrödinger or Dirac equation we saw already today. We plug in it here some basis set and go variational, use the variational approach. And now, depending what you plug in here, you end up, you can use a plane waves as your basis set. You end up to the full variety of pseudo potential methods. You can use a localized states. You end up with FPLO, for example, or you can use some augmented, so you split the space into two regions, the localized-like region, so atomic-like, and the plane wave-like region, and that's certainly one of the best ways. Now, the other way around is to go through scattering. As Hubert showed you, the basic idea, the first KKR implementations were wave function based and were similar road, so they were also using, instead of variational principle as such, were using the scattering theory, so Lippmann-Schwinger equation, or use the newer versions with the Green's function, so which we are mostly nowadays, all of us using it. But what is here happening is very often that you have to linearize, you typically linearize a problem. You will see it in the next slide what I mean with linearization, and you end up by linearizing augmented plane wave method to linearize APW, or you by linearizing the KKR method you end up by the LMTO method. Now, but now with respect to spectroscopy, certainly you know it very well that in the pseudo-potential methods you don't have a core states. There are approaches to improve them, like PAWs, but you still have a problem to describe such as spectroscopies which are core state related. In the linearized method, on the other hand, you have a point that if we set up the space into the, as I said, to the regions where we have atomic-like features, or so this muffin-tin approach, then you end up to this generalized energy-dependent eigenvalue problem, and which is very, very hard. Well, it is very time-consuming. So people were thinking how to get rid of this energy dependence, and the main idea was, let's expand our wave function around certain energy, just a Taylor expansion, plug in in, and you end up with a linearized LPW method or old good LMTO method. And but you will realize very soon here that this is a kind of very good approximation, like any Taylor expansion is a kind of very good valid around this reference energy. And now when you want to do spectroscopy, you would either need a lot of these energies to be included in your basis set when you want to go far above the Fermi level, because typically you are interested in the valence band, so you put your reference energy somewhere in the valence band, many approaches how to choose it. I don't want to go into this detail because I even don't know it, but the main point is the radial dependency of the wave function. If I choose a Fermi level as my reference energy for linearization, and I will go already in the 10, 20 eV electron volts above the Fermi level, it's certainly not good. So that's also limitation which limits many codes to be used for the spectroscopies. I'm not saying it's not possible. Please don't take me wrong. I'm not saying it's impossible. People did a lot of work. There is a lot of work was done to include the higher energies states in the LPW, LMTO, and so on and so forth. As I said, on the other hand, in the pseudo-potential methods, there was a lot of work done to include absorption, for example, X-ray absorption. So that's one of the new features of the VASP, is to calculate the X-ray absorption, which we would before kind of not think about much. So I'm not saying it's not possible, it is, but it takes a lot of work. Now, in the KKR, on the other hand, we have an explicit dependency of our multiple scattering path operator with respect to energy. We have also some approximations to be calculated, as Didier showed, for example, and we want to go to higher energies and so on and so forth. But you explicitly can approach any energy within your approximation, within your potential which you are using. And the potential can be DFT based, but it can be also something else. It can be Hartree-Fock based, it can be something else which is more suitable also, which is then also suitable for excited states. So scattering formalism has a nice feature, and one additional nice feature, and I think I will repeat it once more again, is that the you have to realize one thing. So some of you are using certainly for example, for GW community over there, from Lucia Reining group or the DMFT, you are using certainly the spectral representation to generate the Green's function. And I think this information was not said yet. Maybe it's obvious, but in the multiple scattering, so if you use a spectral representation, you need already from very beginning to have all eigenvalues in the whole energy spectra. In the multiple scattering, you calculate for a given energy without knowing all others, you calculate your Green's function. You don't need to have all of them calculated, yeah? So that's also one thing which makes it very flexible, and I think it was not said explicitly until now. Well, it has a side effects like our irregular solution, but doesn't now matter. But yeah, this is also other aspect why the multiple scattering is so flexible for so this energy which we can approach. And that led certainly in the past and nowadays to many spectroscopies, which has been included in many codes. To calculate many different possible spectroscopies depending and scattering experiments depending on your source, if it's light, if it are the photons or electrons. You can, for example, shoot the electrons here, make a scattering experiment, or you can do spectroscopy on other side in parallel to the thing. Or you can use two kind of inelastic processes, elastic scatterings. So we have a light incident light in, incident light out, the light out, and then you can do also you can look to the other properties. You can look to Auger electrons, for example, if you like, to elastic scattering, inelastic scattering. We will have actually nice talk on the Compton scattering, magnetic Compton scattering of Diana and Diana Benea. So many things can be done. Many things has been done. And now I will try to give you more motivation. So this is I came across. So multiple scattering and birds. So they have these are whatever it is. I don't know. Teresina viridis. I don't know if somebody knows what the bird it is. Swallow 10 egger. I have even no idea in English what it is. Probably from here, John knows it definitely, but for me it's a bird. But definitely you can use this bird, and the people are using the Corringa-Kohn-Rostocker method as we are defined it here, for example, but not for electrons, but for the optics. And they even they have on the one page discussing about the disordered effects on to get this color depending from which side you are looking to it. So and they could calculate the optical reflectance spectrum. So doing, as I said, doing a multiple scattering technique, which Didier already once mentioned it in his slides, but I wanted to show it again. So this slide we also saw, and this gives you the intuitive way of describing spectroscopy, and the intuition there is we have electron, we shoot it there, it is scattered, this we intuitively understand. We have a scattering experiments, for example, or if we have an X-Hubs experiment where you are looking to the nearest neighbor distances, you shoot light, then you get a wave which are reflected back and forth, and you can calculate it by multiple scattering, and really the leading code in this community is the FEV code of John Rare, and he will certainly show us also this in his hands-on course. Now, what are the common ingredients? So, well, the main common ingredient in spectroscopies is the Fermi's golden rule. So we are trying to describe some response of our system to the external field. We suppose we have a weak perturbation, which is quite fine. So we have an unperturbed system. Question is what it is. So it are the states, the ground state, and then we have a perturbation operator, which we at the beginning we don't know how to treat it. Then you plug it in, and you do the perturbation theory for the order, and you get some you get this so-called Fermi's golden rule, which is a classical basic example. And from that day on, the probability, transition probability from initial to final state, we are starting to speak about some transition matrix element, which is here between the initial and the final state. And we have here some energy conservation, which is nothing else. At the end of the day, this gives us, for example, the density of states. You can go further. You can add, if you do some resonance processes in order to describe them, that means you excite your electron through some intermediate state before it goes to the final state. So you can add this and sum up over all intermediate states. Just as very brief. So from this day on, we start then to speak about the matrix elements in the energy conservation. Now let's have a look what is inside. So let's first have a look to the operator. Maybe, I mean, you know it probably for some of you, you did it already in the past, but I wanted to certainly to show you only a couple of points and to show you how we do it in relativistic case, non-relativistic case, and how the matrix elements which we are treating are then calculated with respect to multiple scattering. So we describe our perturbating field so by classical electromagnetic plane wave. Which is over here, certainly with the nice Maxwell equations showing you the electrical and magnetic field part, and we use a Coulomb gauge to typically we choose a Coulomb gauge, which might be not a good choice if you are considering the transition at the surface photoemission. It was discussed in the past, but let's forget about these details. If you would like then nowadays to go really to very intense fields, then you would have to probably go to quantum nature of photon. You will have to consider it. But doesn't matter now what we do it kind of semi-classically, so we replace the momentum operator with this correction. You square it, you get several terms, and at the end of the day, you have this term which you rewrite. So we have a main term is this A dot P term. Then you have this one, we put it because of our Coulomb gauge to 0. And you have some squared, so with respect to the vector potential, some squared term here, which we neglect unless you are doing two photon processes, you should take into account. So our operator, which we are then considering, is just some amplitude times the momentum operator or kinetic energy operator then later on. So we add it in here, just reminding where it goes in here, and you end up with such integrals which you have to solve, which you start to look to it, and we still have this term here, e to the power of I qr, where q is a pointing vector of the light and the r is r. So as a space. Typically we go to so-called dipole approximation, so you can expand this exponential you can expand it and you end up with the dipole approximation, and this is, for example, for photoemission very well fine, because you see the wavelength, it's very far compared, or big compared to the atomic scales. When you go to hard X-ray photoemission, when you go to the X-ray absorption for example, very heavy elements, F-electron systems, then you have to go further out. But generally, we end up always with 1, so it's very easy. You plug in it here. Typically what people then starts to go direction, but this is a really no-go with respect to the calculation, is that you use this quantum mechanical identity, you plug it in here, and you end up here with this very nice dipole operator, which is actually, you have only here wave function and you have a r in between, so you have to integrate it. It looks simple, but it's not really we will see it calculationally very good. Now, when we go to relativistic case, just that you see it as well in the codes, you instead you are using this. So we have a electronic current density operator. So EC alpha alpha we already saw is this Dirac alpha matrix, and so your operator, then typical operator which we are looking for, is this alpha dot A. This is also the form which is very often used in the calculations, for example, of X-ray absorption, transport properties, pinhole effect, anomalous effect, and so on and so forth. This is already good enough to be included. And what is also what you have here is this polarization vector, which can be, for example, Ondra will show it in the case of, if you are thinking about circularly polarized light, it is in this form. So it's X plus minus E times Y. So, and you plug in it here, and you plug it in here, you plug in the initial states in certain, typically in the angular momentum representation, so like hydrogen atom, the final states you can plug in here. And as I said, but when you plug in here the dipole operator, it is really not practical in use because you would have to integrate over the whole space. But what you should then realize here in this structure is that you have here end up with some spherical harmonics here, and when you integrate them, you end up with some angular part of the matrix elements which is responsible for the dipole selection rules or any other selection rules, and then you have the radial part which then modifies it. Now let's look how it looks really in real now. Fully relativistic case. We have this alpha dot A. You end up by the radial part. There are two of them now here. You end up by the angular part, which is over here. Lambda is just the relativistic quantum number. It's combined kappa mu, which we duly showed. It's not important. It's just that you see only this kind of structure, yeah? That you have this radial part, angular part. The angular part is responsible for the selection rules typically, and the radial part is important to be considered. And you see here you have in the radial part here you have a big and small component of the from the Dirac equation, and the angular part looks like that. Well, you have to calculate some Clebsch-Gordan coefficients, and that's what you do. That means when you will realize the code and you will look, for example, to SPR KKR or other than to matrix elements, then at the beginning of the code you will have a call for the angular matrix element, and then later on you have a huge loops to calculate these integrals numerically. So that's, I just wanted to show you. Maybe it's trivial, but just that you realize it a bit. I mean, for students, I think maybe it's good when you have then code in your hand to understand which are the parts are. But not always this alpha dot A for in relativistic case is also good enough. So as I showed you, you can go to the dipole operator using this commutator, or you can use other anti-commutator relations. For example, you can use this anti-commutator relation. You end up by this form of the matrix element. They are equivalent. For example, so alpha dot A you can rewrite in this form, and when C goes to infinity, you will realize you have here then the standard kind of form, which you can then show in this non-relativistic limit that you approach then this A time, well, the momentum operator. Now, for example, these type of matrix elements we are really internally using for X-ray absorption transport. For example, for photoemission, it's not good enough. We have to use other, which we call gradient V. For example, so we have here the potential. So here, and this is what is used, for example, for RPES, all RPES calculations. Now you can ask, well, why it's so? The main point is the nature how we calculate the wave functions, for example. How do we calculate the quality of them? And if you are using, for example, this is obvious with the gradient of the potential. So you wait. So, or let me start the other way around. first thing is also what is for the multiple scattering very nice is always that all these matrix elements, as we split single side scattering from the multiple scattering, that means all matrix elements in this form will be only calculated within the single side sphere or polyhedra, Voronoi polyhedra as case showed, and so on in full potential case. Yeah, so you don't need to go far away. So you don't need to integrate far away. There are exceptions. I'm not saying this, but but generally I would say in many cases. Yeah, and now that means you have to integrate everything within the sphere, and that's already great. If you would think of calculating a matrix element with the R operator in other methods, for example, VASP or something, probably you will have to go to the case space. You would have to do Fourier transform and then integrate everything there over case space integration, and then do it. And this is also numerically not easy. Or in other words, if you would do in real space, you would have to do such integrals because you are working with the Bloch waves, which are really going all over the space. You would have to integrate it over full unit cell. Your matrix element. Now in the multiple scattering, now we are always always many times restricted to the sphere, or to. Am I right, George? I think this is, at least from my point of view, this nice. Also the other advantage of multiple scattering with respect to spectroscopy, and now this particular to matrix elements calculations. And now within the sphere, now you can either use the R. So you have two functions which you multiply by R. So that means you weight as far as when I go from the center, I go whatever 2 atomic units far away. So I weight it by the R. So the main contribution to the integral will come from the end of the sphere. But the wave function itself, there it's not very good because of matching to the nearest cells. If you now use other methods, this alpha dot A, it's a bit better. But for example, this gradient V, which is really essential for photoemission, you see you have a gradient of Coulomb potential. So everything which is here down contributes the most. So everything which is in the near regions of the muffin tin, it doesn't contribute much. So that's why it's also important to realize when you do the calculations for the spectroscopy, which kind of matrix elements you do. Yeah, you pick up. Right. For example, in the case of photoemission, really, if you would like to do you calculate the cross sections. So you know when you increase photon energy or the kinetic energy of the electrons of your final states at the higher and higher energies. If you are using this form, alpha dot A form, you can use it maybe to 200 electron volts, but not higher. If you want, for example, to do XPS, typically which you do in the lab, or soft X-ray, hard X-ray photoemission, which, for example, Fatima does in her beamline, then you need to go to this form, at least for photoemission. And similar restrictions are then connected to other spectroscopies. Okay, but where is our Green's function? So I am speaking here already a long time and no Green's function. So typically when we want to describe our system, we have a bounded states. We heard it already. Those are core states typically, and the final states or the valence states, which are then described typically by the Green's function. So the Green's function itself comes into the Fermi's golden rule when we sum up over final states, use a direct identity, for example. So you end up with the Green's function. So you have some initial state here or final state, depends you are looking for which kind of spectroscopy. I'm sorry, here it's reverted. As you would. I have here mistake, there should be final. But this is but see only the structure. So you will have two operators. You have a Green's function, the imaginary part typically, but it doesn't have to be, and the final state. Now, as I said, we plug it in here. We can calculate it for any energy with some approximation, but it is possible. And then we have these local wave functions, which are then ending up in the matrix element. Now core states, for example, we typically do it when you do SPR KKR. I think John told me also in FEF code, and you do it always relativistically because you want to have a spin orbit splitting of your core states, which is essential, which is huge. Now, multiple scattering path operator. Now we heard it already, but let me summarize it, maybe give it to the context of spectroscopy, okay? So when we want to calculate it, the simplest way or the direct way is to do it in the real space. And this is indeed done for X-ray absorption, XMCD, XAFs, EELs, sometimes XPD, photoelectron diffraction. So, and there you can use many techniques, as Didier showed, for example, to calculate this multiple scattering path operator for the various energies. If I'm more interested now to the solid, then I do 3D Fourier transformation of it, of this expression, and I can now really go to again to X-ray absorption, but also to transport, optics, Compton scattering, Auger electron spectroscopy, positron annihilation, and many other things. So the things which are interesting, if you are interested, or the techniques which are kind of bulk sensitive. Now you can combine it. You can combine now. You can combine the K-space and the real space. So, for example, this is a case when you would like to calculate the semi-infinite surface. And this is done, so within the layer you treat everything in the K-space, so you have two-dimensional periodicity, perpendicular to it, you have a kind of real space, and I will show you how this is more or less done and where the different gradients come in. Or you can use a further Dyson equation, you can make embedding, so when you put here some cluster on the surface, you can calculate the Green's function of your unperturbed system, and you can calculate it for your perturbed system. And this is indeed very used, for example, for scanning tunnel microscopy. We used it for X-ray absorption and XMCD for embedded clusters on the surfaces, and many other techniques can be used here. But this gives you the flexibility of the approach. Okay. And then you will see also in the codes next week that depending which spectroscopy you would like to do, you are interested in, then you end up to the different types of the solving of the multiple scattering path operator. Yeah. Okay. Now in the photoemission, let's be a bit more specific now. When we want to do one-step model of photoemission, we will have a more detailed talk also from Jürgen Braun in I think on Sunday or when it is. And now in the photoemission again, light comes in, electrons goes out due to the photo effect. You measure then you measure the kinetic energy of your photoelectron. You can measure the spin of the photoelectron, for example, which flies out. And the equation looks like that. And the final state, in that case, it's time reversal lead state. So it's scattering state, as Didier showed it, which kind of it's reversed in the time. Didier showed in the very formal way. One can think of my electron anyhow flies away from the surface. So and in the lead it comes in, or other way around. Yeah. Now the final state here, you have to consider inelastic mean-free path. So typically you have to take you have to add some damping of this final state, which goes into the solid. And due to the inelastic mean-free path of the electrons, it is restricted to the certain region of your surface. Now you do the same as I showed you. You plug in here so out of this sum over the initial states, you plug in the Green's function, which describe your valence states. And then you have your final states, which are time reversal lead states. You plug in this guy in, and you can calculate it. The time reversal lead state explicitly, we didn't see it yet, but might look like this. So we have you have a plane wave, and then you have this scattered wave, which you would then expect. And this is the best possible single particle approximation for the final state in the photoemission. At least it's considered to be. Now, but what we need for photoemission, for example, is a semi-infinite stack of layers. And this we didn't see yet. that means now why? Most of you would do slab calculations. So you would take your favorite code. You would, if you want to do the surface, you would take a couple of layers of something. Typically, in order to saturate some charges, you put even a bit of hydrogen below. You have a couple of layers, and then you put a vacuum, a lot of vacuum, yeah, and you repeat it. So you end up with a band structure like this, even though so for example, I have here 33 layers of platinum, so each band corresponds to one state coming from these 38 layers, and then we put it here one cobalt atom on the surface, and you end up here with the spurious state, so with spurious hybridizations of the states, and you might see here some projected region where I have a bulk states. When you do the semi-infinite calculations by so-called, for example, tie-binding KKR or layered KKR method, we will see it in Laszlo Shunyok talk. He will show you how to do it. Now, you see, you get rid of it. You have a really continuum of states where they should be. There are no really kind of hybridization, or there is some hybridization, but already really real with the damping of states, which are now here represented by the smearing. You see the surface state. If you look very close, it's even splitted. So it is splitted due to the spin-orbit coupling. And that means you really need it, and as a photoemission, you would really need to calculate it. So just this is really makes a difference. And just as a side remark, for example, going back to Julie's talk, where we were interested here in the past here was the calculation of magnetocrystalline anisotropy of one monolayer, and there was a really, now I cannot say the numbers, but it was a really quite considerable difference if you do it with a slab geometry or you do it really semi-infinite geometry. So first step is always to solve the single side scattering. So now I want to solve the problem of lead, or problem of this semi-infinite slab of layers for the photoemission. Yeah. So we solve it. We solve the phase shift. We have a D matrix. We have this. You can, depending what you are looking for, but typically we use a single set Green's function. But I want to say here, just that you see in this level, you would add, then you can do it fully relativistically, you can do it with the full potential, you can add LDA plus U, you can do DMFT on the top, so you can add certain type of correlations, or you can do self-interaction correction. And that's what you do. Now on the multiple scattering level, then how you then treat it. So we solve the scattering of one atom, we put it into the layer, we solve, this is then solved in the K-space, so in the two-dimensional periodicity we make use of it. And then we add some plane waves between the layers and solve the multiple scattering between first two layers, for example. So you have a plane wave coming here, it is reflected with certain amplitude, or it's transmitted with certain amplitude between two layers, so all multiple scattering events. And then we pick up these two, put two more and so on, 4, 8 more and so on. So we do so-called layer doubling. For people doing maybe here in the audience something with topological insulators or this direction, this is the same technique as you use to create the surface Green's function in the tie-binding method. Yeah, and then we have scattering properties of the full surface. We can add a disorder. I can very fast go here because Hubert showed it already. And we can do it on this multiple scattering level. So we can do chemical disorder, we can do magnetic disorder by CPA, so put some spin fluctuations, or we can do some structural lattice vibrations, which is but limited to the typically lower temperatures. Let me go, this you saw, let me go here, maybe this you didn't see. Direct comparison now, exactly for this iron pnictide, which I showed at the beginning, you remember, maybe you don't remember, but there was some nice yellow picture. So, but now this is a cobalt doped iron pnictide. This is a supercell calculation as it was done in the past by Vaiku and the co-workers. But they had to use 10 different supercells each, 400 atom each, calculate the band structure, average it, sum it up, and then the next step is certainly if I have a big supercell, my Brillouin zone is very small. So in order to get it to get some information in the Brillouin zone of my smaller unit cell, which the Brillouin zone is then bigger, you have to unfold it somehow. Those procedures are around, and I think some of you are using them, but they are not unambitious. So when there are approximations which you need, and you get really smearing of the bands, you get a shift of the bands due to the disorder, and but when you do the CPA for the same system, you average it only with the 5 effective atoms, so it's much faster, and you get mostly the same information. But mostly, what we really cannot do with CPN is very hard, is, for example, the local relaxation. This one has to say it also loud. This is not included, or it's very, very difficult would be to include it in the calculations. So the CPA disorder can be done, and now but how it's done now for the photoemission, the same as before. We do the configurational average of these Green's functions, which we kind of calculate through the scattering processes. You calculate the single site properties for atom A and B. Then when we do the multiple scattering inside the layer, we do it with the configurational average. You do it then with the layer doubling the same. Some other terms coming up, it's not important. But what is important to realize it here, if I want to do spectroscopy, I can on that level include absorbates, relaxations, rumpled layers, so some relaxation at the surface. I can use the disorder here. As I said, you can use lattice vibrations. You can go even further and include non-local correlations if you know how to calculate the electron-phonon coupling self-energy, or you can go to spin fluctuations. Yeah. So this is then done on that level. That means, in other words, for you as information, and you do the code, then typically this kind of information is done in the section of multiple scattering in the input file. Now, let me come to first example. Because I was asked how we now do include the correlation effects. So I'm going here to show you how we combine the KKR with the dynamical mean field theory, and how it was technically done. So the aim here is to include the local correlation effects. So that means localization of the electron due to the strong interaction, Coulomb interaction. They want to avoid to hop from site to site. So, and typical example are oxides. Favorite one you will see in every LDA plus U talk is a nickel oxide. So nickel oxide is an insulator with a big band gap of 4.3 eV. This band gap comes from these local correlations. In the calculations, when you do antiferromagnetic calculations, you get already some localization due to the antiferromagnetism, but it's not good enough. When you do then the DMFT, you indeed get it relatively very well described, even though one has to say some of the peaks you cannot describe because those are then due to the photoemission process. So this is in this case we are only correcting the ground state. So we do it with the dynamical mean field theory. So it's one of the theories with Václav Jániš was showing you today in this context. So the idea is here you instead of solving the Hubbard model with on the certain lattice, you map it on some effective media. So it's nothing else as a CPA. DMFT is CPA. This I can say, and the DMFT community will tell you it is a kind of CPA. So I can say it's only CPA, nothing else. But no, the point is you embed here some very correlated atom, and there's some like impurity atom into your bath, into your mean field medium, and you can combine it with the LDA. It was showed here. And then we did it also with the DMFT already, well, 2005 or a long time ago. And you can calculate really the effects like localization due to the so metal to insulator transition due to the local correlations. Now, how to solve it? Now, in that case, it's very easy. We have an on-site self-energy. So in DMFT, the self-energy is local. The easiest case is the LDA plus U, which is energy independent. It is just a more or less, it's an orbital dependent quantity. It's one number in the LDA plus U, and you correct doing multiple scattering theory. You can correct our potential because it's local, and then we can add here. You get some. So self-energy is the real and the imaginary part of it. So it's a complex quantity. It is depending on it's an orbital dependent quantity. And as I said, we include it when we solve the single site problem. And this also gives you the feeling that it's this flexibility of the method, because when you add it on the single site level, you solve the multiple scattering is not kind of changed more or less. So you get all access just for nothing. You get to all other parts of the codes which you programmed in the past. And how it's done is just to show you, because we didn't see it. So you add here, you have to solve this kind of quasi particle equation, Schrödinger-like equation, where you have this self-energy. And as I said, it is non-local. So to get rid of it, we project it to some local orbitals, like D orbitals, F orbitals, depending on your problem, like you do in the LDA plus U most of the time. We can solve it, some approximation, but at the end of the day, you get a Schrödinger or Dirac equation, depending what you do, with the additional term which you add. And this leads to Green's function which you calculate. And then now, in order to get the input for a DMFT, which is so-called Green's function matrix, we project it again to the same local basis. It can be orbital, could be some linear functions. So there are possibilities how to do it. We do kind of really localized orbitals which are sitting on a given atom. It's a scheme. So, but let me look to results. So here I'm just going back to the yellow pictures I showed you at the beginning. So to the Fermi surface of potassium-doped iron pnictide, which is strongly correlated. The black lines are really measured, quantitatively measured isosurfaces of the experiments, just better to compare it. And you see when we include the DMFT, we get much better description, for example, in particular here around this X point, which is connected to the orbitals of iron, which are in the LDA or GGA2, are below the Fermi level, and you can't see it very well. We did other things. For example, you can combine it with the CPA again. We had a look recently to the high entropy alloys, where here you have a photoemission. It is measured at 75 eV. And you see that you have here some satellite-like feature, which in the LDA you don't get, and some shifts of the states around due to the correlations, due to the very strong localization in this very disordered alloy. So this is an alloy of 5 elements. Each element is with a 20% insight, and you can apply it for it. Yeah. I think Hubert was not involved in that work. They did a lot of work on the transport side together with the Oak Ridge on these kind of alloys. Okay, good. Let me come now, just remind you back what I showed you, Fermi's golden rule, initial, final state. We plugged it in here. We had a look how one of the possibilities how to solve the multiple scattering part, particularly in the photoemission case, but I showed you other cases as well. And now, just first thing which I would like to, based on this example, would like to show you are two effects. and I will come to it. So inclusion of the thermal vibrations, and the other effect is why we don't take some simple final state. Okay. So now let me come back what I want to show you. So what I want to show you is the high energy photoemission. So you know, and I think Keisuke mentioned it, and it's pretty obvious when you are looking to the inelastic mean-free path of the electron as a function of kinetic energy, you will very soon realize that you get this so-called universal curve, even though it's not universal, but people call it. You have this banana-like shape always, and the typical photoemission experiments are down somewhere here. So you are your photoelectron, which you excited, cannot escape from very deep from your solid. Now, looking here, clear idea is now let's go to soft and hard X-ray, and I'm getting more and more bulk sensitivity. But there are important aspects. You can really now start to do it. This was started the whole development, and was really also connected to the developments of the synchrotron radiation sources, to the developments of the detectors, and so on. So these kind of experiments were possible. So first, 2005 started slowly many experiments in this way. But there are important aspects which you need to include it when you go to this, and one of them is a thermal vibration, another one is that free electron-like final state is not enough, and the third one are so-called sample tilts. Okay. Now there was a proof of principle that you can really do it. You can do it even with very high energy, so going to 6 kilo electron volts. You can measure, for example, the band structure, bulk band structure of tungsten, and compare that time to the theory. And that was at the beginning. Now, why can we use free electrons? Because the idea is certainly when we now go to the high energies, the inelastic mean-free path is here becoming you go more and more deep in. So you're kind of broadening in the K space, which it's proportional to the inverse of this. How far the final state goes in is better and better, and by varying photon energy, for example, you can really cross your Brillouin zone, and you can measure your band structure depending on the so-called KZ value. So going up in the Brillouin zone, because photoemission is done at this surface, so in order to get this direction, you have to change the photon energy. And the point is, we want to look to the surface. And now when you look here and you go along this direction, you should see some circles and some necks where no intensity is. Now when you do the experiment, you see we go from 400 eV to 1200, where most people would tell you it's already free electron-like, but not you see some things where the neck is, where no intensity is in. And there is even more, you see some states which are appearing here, which shouldn't be there. When you look to the simple Fermi surface, this should be sphere or modified sphere. Yeah. So those two features, and when you do the full theory, you get it. And you see when you do the simplest approximation, you would first try to do the free electron-like, you don't get this state. So this is really due to the final states, due to the smearing of the final states, and some additional channels in the transitions which you get from other KZ values. So one have to be careful saying that going to high energies, your free electron-like is good approximation. It is already better than nothing, but yeah. Now the other aspect of the hard X-ray photoemission is the temperature, and that's where we started that time to think about how to include them, and it ended up to this, I would say, alloy analogy model, which was coming in. But the main point is we have, by increasing the temperature, you see you get smearing more and more the data. So when I do the certain cut here, for example, at two angles, at a certain angle here, you see you get increasing the temperature, you get the more and more density of states-like features. So instead of your band structure, instead of your spaghetti which you would like, you get density of states and you are unhappy. And this effect we wanted also to include. And there are possible ways to do it. Very long time ago, people, so first of all, this averaging over the Brillouin zone due to the excitations in phonons or virtual phonons was already a long time ago predicted. And you can describe it by some kind of linear combination of these direct transitions, so K-dependent, and indirect transitions, K-independent. And the simplest approximation you know probably also from scattering techniques, that you add up some Debye-Wohler factor into your single-side scattering and try to solve it. But it is not enough in this case. So what we do, we say that our system, we have vibrations in the system. The atoms are vibrating. I'm saying vibrating, really not phonons, because those are already uncorrelated movement of the atoms in that temperatures and these regimes. You average it, all of them, take average over the temperature, and you can work on that. And indeed, you can get these effects out of it. Maybe, well, I don't know too much to these details. Now, we did also, what is also, you can go further. You can, for example, look at the surface. If I have a surface, then the vibrations in the layer and between the layers are different, so you don't have a kind of a regular distribution of these vibrations. You get some ellipsoid. You can take this into account. You can calculate the vibrations by density functional perturbation theory, as we did it together with Matthew Verstate. And then indeed you can get the effect of the surface vibrations, and which is quite considerable here. So this is bulk-like and this is a surface-like. So now you can ask me now, but you said we are bulk sensitive, so it doesn't matter what is surface happening. But it's not true, because the photoelectron has to escape also through the surface when it's approaching to the detector. So it will be average also, and we'll see this as well. It can be then used further. So Hubert proposed that time, let's now include also spin vibrations and have a look to the very old experiments which were done in the spin result photoemission of iron from Kisker, which were not kind of described much. And there are not really many temperature-dependent experiments done in photoemission, because you don't want to do it because you spoil your detector and your vacuum. You don't want to heat it up to 900 K. I don't know why they did it at the time. Maybe just throw it away. But definitely, when you include this kind of spin vibrations and the lattice vibrations in the spectroscopy, you can then describe very nicely the spin-dependent photoemission. Now I am showing it. It was also because you can see there's a motivation for pump probe experiments, which are down nowadays. Where you are doing ultra-fast, you're looking to the ultra-fast response of your system to the pump pulse. This was done, for example, here in Jülich, where they were discussing the different scenario when I pump the system. So I excite the electrons. How do they demagnetize and so on due to the different Stoner-like or Heisenberg-like? I don't really want to go to details. I just want to point out that we didn't describe it here during this workshop, but people who are more interested also to multiple scattering formalism and going to the time-dependent phenomena, and by doing multiple scattering in the Keldysh formalism, so calculating 2 times Green's function, so they should then go to Jürgen or to Hubert if you are need to more discuss this, because we didn't have this here presented. So if you want to go that direction. Okay, and the third one, which we also now we are working on, is bit now. In the hard X-ray photoemission, that is extremely important, and soft X-ray as well, how your geometry of your experiment is. So if I have a surface and I plug in, I don't know if you ever saw the typical sample plates for photoemission, so they look like that, but much smaller, centimeter by centimeter. And now you put here something. you put here your two-dimensional system, like, for example, some dechalcogenide, transition metal dechalcogenides is very popular. You pull it with your tape to get a clean surface, but you really don't know how the thing is lying here. That means the surface of your sample is certainly not parallel, probably not parallel to the sample plate. Yeah, and in standard photoemission measurements in the UV regime, it's not the big deal. But when you go to soft and hard X-ray photoemission, it's a big deal. And what is big deal is that instead of you are thinking you are running around gamma K direction, you are running in the 5th Brillouin zone along gamma somewhere. Yeah. No, I wanted to say, I extra didn't want to say high symmetry point because you are running somewhere. Yeah. That means that's extremely important, and you do not know it from the experimental point of view. Yeah. So you measure nice your picture, so something like this. Yeah. And now you need to know where I am to understand it. And just one example, we are working on that. So Fug has a poster on it, is a thallium arsenide. It is a typical example for Weyl fermion. So you have here certain crossings of the band structures. There are two types of them. So two types of crossings here, and you would like to see them. You need to have a bulk. So they are connected to the topology, and you need to have a bulk sensitive technique in order to see them. So that was done indeed for a soft X-ray photoemission on the beamline actually where Fatima is, so in Swiss Light Source, and you can nicely measure it. Those points are now connected by surface state, but I don't want to go to this detail. But we wanted to see both of them, yeah, and it was not done before. But then we realized we do the experiments and we have really problems to interpret it. So we went to the hard X-ray photoemission and soft X-ray to see many of these Weyl points. So that's why we had to set up now the technique to use a generic genetic approximation, which for me it's a black box. It's kind of artificial intelligence tool in Python, whatever. I really didn't have time to deal with this in much detail. But the idea was really to combine to have an experiment to first to try to get the parameters of the experiments by free electron like final state, but as I showed you, it's not enough. And then to use this further to calculate the one-step model and to have it in one loop and to avoid as many calculations as possible. That means you want to make this kind of fitting in the really term of genetic approximation, and it takes really couple of calculations to get it. And indeed, this is what you get. So you give the code. The only thing what you give the code is experiment, this blurry thing, and then it calculates the free electron-like. So band structure of, in this case, this thallium arsenide, and tries to find the best fit. You will realize it's not so easy in the case of such a spectral function. And then you can do, it means you get some tilt, you get some information, and you can prove it by the experiment. So this is really our fitting or our procedure when we take the spectra as calculated by one-step model, so this color map which is in the background, and then fit it by our procedure, and we calculate it for a tilt, whatever it means, for a tilt 1.9, and really we get the best agreement with the band structure with the 1.9. Certainly you can ask why there are shifts, but those are all matrix elements, final state effects, which are not included in this free electron-like picture. So what I want to say, the multiple scattering can be also used, even though it's sometimes so slow, but it can be also used in this, big data movements, which are nowadays used here. Okay. I think I will stop here. I will stop here because I have still too many things to be showed. No, no. I wanted to show two more things. One was connected to the relativistic effects and calculation of the spin polarized photoemission, but this Jürgen will show. But the second one was about the matrix elements. We were speaking all the time matrix elements, how do they calculate it, and I wanted to show you some linear dichroism. But it's not important. This is, I just wanted, it's better to skip it now. But I wanted to show you really some ingredients and to answer already some questions I got over the things that over the workshop now. That's why, as I said, it was a bit chaotic in the sense of this sense. I didn't have a nice closed talk. But the main point I wanted to show you were the ingredients we need and how we solve the matrix elements, which forms we are using, why we are using it, why we are using a multiple scattering for the spectroscopy. And you will now see and how we include the correlation effects. And then we will see various really detailed talks, for example, for Diana on the Compton scattering, from the Christine Richter, we will see really how the experiment is done in spin and time resolved photoemission. From John, we will see various calculations for X-ray absorption, EELS, REX, but going indeed the direction of including the temperature, as I understood, including the further correlation effects for the final state and so on and so forth. And Jürgen will then show the relativistic theory of photoemission, so it will bit overlap what I said, but we agreed on some parts which I show and which he doesn't show, so I hope the overlap will be as small as possible. Then Ondra will then speak about the X-ray absorption, but with this X, what it means, so the linear dichroism, XMCD, XMLD, that's why I also skipped one of the examples I wanted to show you. Then we will have Madalena using again as a point of view of experiments, using the multiple scattering. So the second experimental talk. So we will have now for two experimental talks. We will have now Peter Kruber, who will speak then further what Václav Janis showed you. So he will then speak about Bethe-Salpeter equation and multiple scattering. And then the codes which we have are also very dedicated to the spectroscopy and SPR, KKR, GNAX, and the combination MS spec and SPR, KKR, the ASE. And then we will have also nice, those are hands-on course, but we will also nice talks on presentations on other codes like FEF code and scattering code from Benfato and others on Saturday. So thanks for your attention. And let's go for dinner. If you have questions, you can ask me. We can speak them further in dinner. Yeah, Didier?
Yes, in your genetic algorithm exploration of the parameter space, you just focus on the tilt.
No, not only. Not only. You need also to explore the tilt, the incoming light, because in the hard X-ray photoemission, it is important the photon momentum, because in normal experiments you ignore it, but I mean in the UV regime, but in the hard X-ray photoemission it is important. So when I have a tilt, then it might change a bit. So tilt and then also bit you can also think of correlation effects if you like. So at least the Alex wanted to have it some kind of renormalization of the bands. But this can be then thrown away. That was also one of the points which we wanted to then discuss. Also that can be also included as an additional experimental parameter. So depending on your exit slit, so which goes into your semi-sphere, depending what you use here, you will get a different broadening of your data in addition. Okay. But not simple broadening, but also energy and also the momentum broadening.
But purely experimental parameters.
Purely experimental parameters, yeah. But you need to consider it in order to know how your experiment was then done.
So
John.
can I ask a question
Surely,
on
surely.
convergence? So you said there's really no problem to do XAFs. How high up in energy can you go? And what
So the trick is here. So let me start other way around. The one could use also the techniques as Didier or you are using. This we didn't do. What we did here was we were using single site scattering approximation for the final state. And when we go even to higher energies, you can even go further to set it to 1. So when you invert the matrix, you know, for the so with the Cambe lattice sum, so 2-dimensional lattice sum, and you invert it, then this inversion you can either for high energies show that it's like you can approximate it by so well now I do 1 plus t times x, or then you can ignore multiple scattering and use a single site scattering. But there is a but. Why it works so nice here? In addition, it wouldn't work for XAFs, for example, X-ray absorption very well. But here it's good because we still keep the whole kinematics of the.
Recording stopped.
Thanks. Kinematics of the final state. Then it is still. Depending on the k plus g parallel vectors. So we get still photoelectron diffraction effects, even though a bit approximated by this. But for the photoemission seems to be good approximation enough. And with Didier, we would like to look to it more in detail, where he is solving it in more better way in real space, but more he showed his things, the algorithms, and also a bit to compare it with the soft X-ray. I mean, for the photoelectron diffraction then. But yeah, that's as it's done now in the photoemission. Yeah, Unra.
I'm just surprised that you are saying that you cannot use this free electron approximation for energies up to 400 keVs. I mean, you showed some examples that it doesn't work. I have to admit, still, it somehow doesn't intuitively.
Yes.
Honestly, I don't like it.
Maybe it's a bit connected.
Explanation, or what's the point?
Well, in the photoemission, the point is that it is still a damped wave which goes in. That means you have still some KZ broadening. That means, in other words, you have a transition. You would expect that you have a transition from this point and the band which is appearing it, but you get also transitions from somewhere else as you expect. Yeah. That means, in other words, here I had my Fermi surface here. Yeah, and I was expecting to get transitions only from this cut. Yeah. I get some contribution from somewhere up and down as well, which you wouldn't expect, or you, in the free electron-like case, you wouldn't have it. For example, as one of the examples. And this goes further. This is also seen in LEED. There were nice works of Vladimir Strokov, for example, where they were kind of looking, and with Evgen Krasovsky, who did one-step model photoemission on LPW level, where they were looking to the LEED experiments and exactly to such effects. And they showed it also very nicely. It was now I have to be careful which molybdenum diselenide? No. Titanium selenide? Something. Yeah. Right, where they also showed that when they were going even to higher energies in the LEED experiment, no photoemission, yeah, that the final state is still far to be free electron-like. Experimentally proven by LEED and shown by also calculations. So, but in some respect it might be connected to photoemission. There are other techniques which might be not the case, but I show it always because people very like to, there is a strong movement in community and it's better than nothing. they starts to use a free electron approximation to describe the photoemission and really add this matrix element, which before it was said it's 0, it's 1, you know, to calculate it on this level. And to describe dichroism, spin polarization and such a things, or orbital polarization. And then, but like this, there are things ending up on the top. I think Jürgen will show it more.
Okay. What can I do?
Well,
But you think that those features, they are completely related to the photoelectron effect, or like technical things related to the photon energy?
no, it's a real.
I would say it's really related to the photon source.
No. It's more. It's really related to the nature of the final state, which you have. Because you see it also in experiment. It's not only related to the theory, but it's also and some photon source, but also you can see it in the different experiments, for example. At least in this case, yeah. So thanks and yeah, surely, yeah, sorry.
A simple question about your implementation of the KKR code. And I saw from your device that when you combine with the MFT, and you only add the MFT cell energy, but you didn't remove the coordination energy from the combination. What's the reason?
No, we remove the double counting is taken account. On the usual way, it's done on this level. So we do typically, so well, what is done typically, or how we do it very often is now we calculate the self energy. You get also static part of it from flex, TMA, or whatever. You subtract it completely, and then you add on the top the LDA plus U static part. It is equivalent more or less to the double countings which are used around. So we were doing some other choices. There were also some proposals to have some average spin double counting, or I can show you on the formulas. I mean, I don't have it here, but it is certainly you have to correct it. No, that's for DMFT you have a U as a parameter and you have a double counting as a. You don't know how to treat it. That's true. You would have to go to DMFT plus GW to get it out of it, like Silke Birman did and many other people nowadays. So, but on that level, it's done on this way. Yeah. Okay, so thanks. Otherwise they will close us.